Pericyclic reactions. Organic reactions can be classified under three different heads. The first one is the polar reaction, which is the most common type of reaction. In a polar reaction, a new bond is formed using two electrons from the nucleophile. So here is an example for the polar reaction where you can see that the hydroxide ion is going to act as a nucleophile on this alkyl halide. We know that the alkyl halide is a polar molecule where you can see that this carbon right here is going to have a partial positive charge and the bromine right here is going to have a partial negative charge. Because of this oxygen with its lone pair of electrons is going to go and attack this electrophilic carbon, thrust these electrons onto bromine to form the compound that we want. Here, the two electrons which are needed to form the bond is coming from the nucleophile. So these type of reactions where two electrons are going to come from one reactant, it's called as polar reaction. The second type of reaction is a radical reaction where a new bond is formed using one electron from each of the reactants. Here we have an ethyl radical. The ethyl radical will react with chlorine, which means this chlorine needs to donate one of the electrons towards this ethyl radical to form a bond between carbon and chlorine. So here is a new bond that is formed, and the remaining one electron from this bond is going to go on to this chlorine to form the chlorine radical. The third type of reaction happening in organic compounds is the pericyclic reaction, where electrons in one or more reactants are reorganized in a cyclic fashion. Because the reactants are reorganized in a cyclic fashion, this is going to be following the concerted mechanism, which is going to result in a single transition state. Concerted reaction is a reaction where bond breaking and forming all happen at the same time. There are different types of pericyclic reactions. In this video, we'll talk about these three important pericyclic reactions, namely the electrocyclic reactions, cycloaddition reaction, and sigmatropic rearrangement. Electrocyclic reactions. An electrocyclic reaction is an intramolecular reaction in which a new sigma bond is formed between the ends of a conjugated pi system. We are going to take 1,3,5-hexatriene as the example, where you can see that there is alternate double and single bonds. Here, at the expense of one pi bond, one new sigma bond will be created. When this compound is subjected to heat, what's going to happen is the electrons from the pi bond is going to shift in here to form a new sigma bond. So these electrons are going to shift in here to form the new sigma bond between these two carbons. And at the same time, these electrons from the pi bond is going to come here to form a new pi bond. Okay, and this pi bond is going to shift here to form another pi bond. This is going to result in a cyclic structure. Let's draw the structure. Now you can see that here is a new carbon-carbon single bond that is formed. Let's highlight this. So this would be a new carbon-carbon single bond, sigma bond. And this is where our new two pi bonds are created. These are our two pi bonds that are created. Now you can see from the product there is fewer number of pi bonds. In the reactant you have 3 pi bonds, whereas in the product you only have 2 pi bonds. And also it's easier to identify the electrocyclic reactions because the product is always going to have one extra ring in this reaction. So in an electrocyclic reaction, one sigma bond is created, one new sigma bond is created at the expense of one pi bond. Electrocyclic reactions are generally reversible, in which case one of the sigma bonds is broken and in place of it is created one new pi bond. So here, if we want to show the shift of the electrons, so this bond right here is going to break and these electrons are going to come in here. So this is going to result in a conjugated pi system. So this would be the product that will be obtained, which is 1,3-butadiene. The next set of reactions are the cycloaddition reactions. In a cycloaddition reaction, two reactants come together to form the cyclic structure. Remember, in an electrocyclic reaction, there is only one reactant which is forming the cyclic structure. But here in the cycloaddition, there are two reactants that come together to form the cyclic structure. The most famous cycloaddition reaction is the Diels-Alder reaction. Diels-Alder reaction is an example for a 4+2 cycloaddition reaction where 4 electrons from the diene, so this is the diene where you can see that there are 2 double bonds and they are conjugated, and this is the dienophile, the lover of the diene, and there are 2 electrons present on it. So if you take a look into this, so there are 2 pi bonds. So each of this pi bond is going to have 2 electrons. So on the whole, it's going to be 4 electrons. And in the dienophile, the pi bond has, there is only 1 pi bond, and this is going to have 2 electrons. So therefore, this is called as 4+2 cycloaddition reaction. Now let's see how the movement of the electrons takes place. So the pi electrons from the diene is going to attack this carbon, and these electrons from the dienophile is going to go and attack this carbon, and the electrons from the pi bond is going to shift in here to form a new pi bond. So in the Diels-Alder reaction, there are 2 new sigma bonds that are created. So here are the 2 new sigma bonds that are created, and there is 1 new pi bond that is created. So let's write down the structure that we'll be getting. So here is the structure, which is basically a cyclohexene molecule. And if you want to number the carbons in the diene, so this is going to be 1, 2, 3, 4. And if you're going to name this as A and B. And you can see there is a new double bond that is formed between carbon 2 and 3. And these are our new 2 sigma bonds that are created. And this is our new pi bond that is created. Okay. So in Diels-Alder reaction, there are 2 sigma bonds that are created and 1 new pi bond that is created, resulting in a cyclic structure. The last set of reactions that we're going to talk about are the sigmatropic rearrangements. In a sigmatropic rearrangement, a sigma bond is broken in the reactant, and in place of it is created a new sigma bond. But the number of pi bonds in the reactant and as well as the product is going to remain the same, but the position of the pi bonds is going to change. Let's see how the electron shift happens. So here we are going to break the sigma bond from the middle of the conjugated pi system. So this is the bond that we are going to break. So this is going to shift. This sigma bond is going to break and it's going to shift here. And these electrons from the pi bond is going to form a new sigma bond. And this is going to shift in here. Let's write down the product here. Here is the product that is obtained. And you can see that this is a new sigma bond that is created. Okay. And this was the sigma bond that was broken. Now this particular sigmatropic rearrangement is called as 3,3 sigmatropic rearrangement. Now what's the meaning for this 3,3? So let's take a look into this. This is our new sigma bond that is created, and our old sigma bond was here, right? So between these 2 bonds, how many atoms are involved? So this is 1, 2, 3, right? So this is 3. The first number is going to be 3. And then like when you go in the other direction, this is also going to be 1, 2, 3. So these numbers are going to represent the number of atoms that's going to be in between the 2 sigma bonds. Okay. So let's do this. It's going to be 1, 2, 3 when you go in this direction, and again it's going to be 1, 2, 3 when you go in this direction. So these are the numbers 3 and 3. Let's go on to the next example. The next example is an example for a 1,5 sigmatropic rearrangement. Now let's see why this is going to be a 1,5 sigmatropic rearrangement. Here the sigma bond is going to break at the end of the conjugated system. So it means we are going to shift these electrons onto here to form the pi bond. This is going to shift in here, and this is going to form a new bond here. So there will be a new carbon hydrogen bond that will be formed here. This is a new sigma bond that is formed, and this is the sigma bond that is broken. So let's write down the product. Here's the product that is obtained, and let's justify why this is going to be called as 1,5 sigmatropic rearrangement. So when you take a look into this, this is a new bond that has been created, right? And our old bond was here. Now, if you count the number of atoms that is involved in between the sigma bond that is formed and the old sigma bond, you can see that there is only 1 atom. So basically, it's just this hydrogen, right? So this is a new sigma bond, and there is only 1 atom here, right? So in the same way, when you go in the other direction, so let's kind of take a look into this. So when you go in the other direction, so this is 1, 2, 3, 4, 5. There are 5 atoms that are involved in it. So you always needed to put the smaller number first and followed by the higher number. So this is going to be called as the 1,5 sigmatropic rearrangement. So keep in mind you're taking a look into the number of atoms between the new sigma bond and the old sigma bond in both the directions, and that's what we did here as well. So this is the new sigma bond that was created, right? And this was the old sigma bond. So between this, you're seeing like 1, 2, 3 atoms, and it's the same like when you go in the other direction also. But here that wasn't the case. Here when you reach from here to here, this was just one atom. But when you go from here to the other side, where the old sigma bond was present, it was 5 atoms. So this is going to be 1,5 sigmatropic rearrangement. Here are some more examples for the 3,3 sigmatropic rearrangements. When you have only carbons in the 1,5-diene, then it's simply called as the Cope rearrangement, where you can see that this is the sigma bond that's going to be broken. So this is going to shift in here. These electrons are going to come here to form the new sigma bond, and this is going to form a new pi bond. So you can see that this is the compound that is obtained, and the number of pi bonds is remaining the same, but their location has changed, and a new sigma bond has been created at the expense of the old sigma bond. But when you have an oxygen in between the two double bond, then it's going to have a special name called as Claisen rearrangement. But the shift of the electrons is going to remain the same. Keep in mind that this is the sigma bond that's going to break, and it's going to move towards to form a carbon-oxygen double bond, which is going to be relatively more stable compared to the carbon-oxygen single bond. And then these electrons are going to shift in here to form the new sigma bond, and this is going to shift here to form the new pi bond. So again, the number of pi bonds is going to remain the same, right? So here again, we have 2 pi bonds, right, in the product also. But keep in mind that this is a carbon-carbon double bond, but this one right here is a carbon-oxygen double bond. So that's the basic difference between Cope rearrangement and Claisen rearrangement. In Claisen rearrangement, it will be, the starting material would be allyl vinyl ether. So if we take a look into this is our vinyl group, right? Because this is an sp2 carbon, right? And this carbon right here is an allyl carbon, because you do have a vinylic carbon right there. So while this is an vinyl group, this one right here is the allylic group. And therefore this is called as allyl vinyl ether. Here is one more example for the 3,3 sigmatropic rearrangement. When the starting material is an allyl ester, then it has got a special name called as Ireland-Claisen rearrangement. So this is a carbonyl compound, and we know that this is an alpha carbon. So basically there is a methyl group, and one of these hydrogens can be easily pulled away by the base, right? So when it is pulled away by the base, it's going to form the enolate ion. Let's draw the structure of the enolate ion here. So this would be the enolate ion that will be formed, but this will be resonance stabilized, which means this is going to go form the double bond here, push in the electrons onto oxygen. So this would be the other resonance contributor. And this is reacted with TMS chloride, which is trimethyl silyl chloride. Trimethyl silyl ether will be formed. Okay, this is trimethyl silyl ether, which when heated can undergo the Claisen rearrangement, where this is a sigma bond that's going to break, and it's going to move towards this carbon-oxygen single bond to form the carbon-oxygen double bond. And these electrons are going to hop in here to form the carbon-oxygen single bond here. And this is going to hop in here to form the new carbon-carbon double bond. When you react it with mild acid, this is going to get converted into OH. Here again, you can see that the number of double bonds are going to remain the same. There are 2 double bonds here, 2 double bonds here, and at the expense of one sigma bond, a new sigma bond has been created.